a thumbs up. That does encourage me to keep making them since I know they are beneficial. On the flip side, if you think there is something I can do better, please leave a constructive comment below the video on YouTube, and I will try to incorporate those comments into future videos. And finally, just keep in mind that these videos are geared towards individuals who are relatively new to stats. So I will just be going over basic concepts, and I will be doing so in a very slow, deliberate manner. Not only do I want you to understand what's going on, but why. So all that being said, let's go ahead and get started. Now, this video is the next in a series of several videos I have done on different types of probability distributions. So we've talked about the binomial distribution, we talked about the Poisson distribution, and this one is probably the most important for your use because we're going to talk about the normal distribution. And if you've had stats or you're currently in a stats class, I'm sure you have heard about the normal distribution. You probably have heard of the idea of the bell curve. And this is the same idea. The normal distribution is probably the one we use the most in first year stats classes. So it is by far the most important thing to understand as you get into higher level statistics or more advanced topics even in that first year, because so much is based on understanding the concept of the normal distribution. So let's go ahead and talk about it. Now, a quick review about continuous probability distributions. So in my previous video, we talked about uniform continuous probability distributions. Now we know that the total area of the distribution has to add up to 1. And then for this continuous uniform distribution, any point beyond the edges is 0. So all of our area, all of our probability is in this rectangular shape. Now a continuous probability distribution, a uniform one like this, we give one end A on the left, we call the other end B there on the right, and then we talk about the width of this rectangle. Well, the width of the rectangle is B minus A. Of course, the distance to B from the axis minus the distance from the axis to A leaves us with the distance between A and B. So that is the width of this rectangle. Now we know the area is 1. So just using some very simple math, we know that the area of a rectangle is its height times its width. In this case, it equals 1. So we know 2 of those things, so we can solve for the third, which is the height. So we use some simple algebra to come up with the height of our distribution here. So it's 1 divided by B minus A. So that is the height of this rectangle. The area is 1, the width is B minus A, therefore the height is 1 divided by B minus A. Now, with this continuous uniform distribution, we talked about a very important concept. The probability of any specific outcome in a continuous distribution is 0. And we'll review why that is here in a second. All we can do in a continuous distribution is find the probability over an interval of outcomes or a range of outcomes. So think about this. Let's say, well, we know this entire rectangle, the probability has to equal 1. Now that's divided in half, right down the middle. So we know that 1/2 is going to have a probability of 0.5, the other half will have a probability of 0.5. Well, that's 1 over 2. That's very simple. Now what about if we divide it into 4 equal bars, right down, up and down, vertically? Well, that's 1 over 4. So each bar would be 0.25, the next one 0.25, 0.25, and 0.25. Now let's say we divide it into 10 bars. Well, that's 1 divided by 10. So each bar would be 0.1. Let's say we divide it into 100 bars. Well, each bar has a probability of 0.01. Divide it into 1,000 bars. Divide it into 1,000,000 bars. You see what's going to happen here? As we divide it up into more and more vertical bars, they get more narrow and more narrow and more narrow. The probability goes down, 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 down. And as that happens, as we divide it up into an infinite number of bars, the probability of any one of them approaches 0. So in real life, the way to think about this in terms of continuous data is maybe you had a chemistry class and you go over to the scale and you weigh a chemical on the scale in the chemistry lab. Well, that scale may have 3 or 4 or maybe even 5 digits, past the decimal point. Well, it's the same concept here in continuous data. The probability of any specific outcome is 0 because the decimals could keep going on forever. So that's the difference between a coin flip or a die roll, which has 2 and 6 outcomes respectively, or continuous data, which has an infinite number of outcomes, and it's only limited by the precision of whatever measuring instrument you are using. Okay? So the idea of any given outcome, the probability is 0, therefore we can only find the probability over a range of outcomes, is fundamental to understanding the normal distribution. And that's why I spent 4 minutes explaining it, in case you didn't watch the video on that this slide is in on continuous uniform distributions. So, you've seen this shape before. I bet you have. Maybe something like this. And in the front or back of your book, your stats book, you've probably seen something like this with a whole bunch of crazy numbers all over it. It has the bell curve there, and it has percentages and deviations and z-scores and t-scores and stanines and all kinds of crazy stuff. But oftentimes, you don't really understand where this stuff comes from. So the idea of this video is to we're not going to explain everything in this graphic right here, but we're going to explain several things in it so you can solve problems using the normal distribution. But I'm sure you've seen this before. So what about the normal distribution? So oftentimes data is described as being normal in the statistical sense, but what does that mean? So let's talk about the frequency by which some events occur, both natural and man-made. So some natural things, human, the height of an adult human, the temperature outside, a person's blood pressure, etc. So those are events that occur in nature that tend to follow a normal distribution. Or man-made, machined products, maybe in quality control situations, financial data, sales data, and things like that in business. For these measures, the average or the mean tends to be very frequent, while measures away from the mean are less and less frequent. So the data in these situations tends to clump around the mean. So let's take a look at the normal distribution and learn more about its properties. So here it is. Now, from at least my view, from an aesthetic sense, in terms of something being sort of attractive, I guess you would say, I think the normal curve is a very aesthetic shape. But there are some things about the shape we should know. On the ends, we call these the tails. So we have the lower tail and the upper tail. Sometimes you'll just see here the tails. Underneath the curve is the probability area. So everything under the curve is what we're interested in. We're not interested in anything outside of this curved shape, just the area underneath it. Another characteristic of the normal curve is that it is symmetric. So it has symmetry down the middle. So the left half is the exact same as the right half when we're talking about the perfect theoretical normal distribution. Now the high point, or the top of the normal curve, is the mean, the median, and the mode. So the top of the curve there is the same. So the mean, the median, and the mode are the same thing. So right there. Now the mean down at the bottom just tells you where the position is of your normal curve. As far as the shape goes, that's largely affected or largely influenced by the standard deviation. And we'll talk about each one of those here in a minute. So the two parameters that really give the normal distribution its position and shape are the mean, mu, and the standard deviation, sigma. So let's talk about the mean. So I've used just the standard normal curve here, so I've set the mean to 0. Of course, there's no axis at the bottom to tell you that. But we'll just say the mean of this curve is 0. Now, I could slide it over to the left. So a mean could be negative 12.3. That's fine. So the mean just kind of slides it over to the left. Or we could have a mean of 10, and that would slide it over to the right. So the mean here can be any numerical value. And what it does is it slides the entire distribution side to side, left to right. And this is very, very important later on when you are trying to determine if two samples or two populations have statistically different means. So maybe you are doing an experiment and you have one group or one, something that gets the experimental treatment and you're expecting something to increase. Then you maybe have a control group where you're expecting no increase. So you would be interested if the means in these two groups are statistically different or have significant differences, statistically speaking. Well, that's what we're talking about here. Now, it would also have to do with the variance, but if the curves are very far apart, the means are far apart, then you might have some indication that whatever experimental treatment you did affect that group. Okay? So the mean just slides the distribution side to side. Now, standard deviation, in many ways, is more interesting, at least I think. So what it does is it gives the curve really its overall shape. So this is sort of our normal curve. Now this shape, as you can see, it is taller in the middle and narrower on the sides. If our standard deviation is smaller, it makes that curve more narrow and taller. So you can see sort of the grayish blue curve is below the orange one at the bottom, and it's above it at the top. And just keep in mind that whatever area difference is at the low side, it's the same as the difference there at the top, or that it goes above. So just a smaller standard deviation will make the curve, assuming the same mean, narrower and taller. Now the opposite is also true. If the standard deviation is larger, it will flatten and widen our distribution because our deviations on average are further away from the mean. So the standard deviation gives us the shape in terms of how sort of short and wide or narrow and tall the distribution is, and of course the mean slides it from side to side. Let's talk about a few more things here. So here is our standard normal curve. And I went ahead and highlighted the area underneath it all in red. And this is a specific type of curve called the Z distribution. It's called the standard normal curve. And that just means we standardize our distribution by making the mean 0 and setting the standard deviation to 1. So again, you'll often see it called the Z distribution. So down below, we can see that we have 0 as the mean, and then we have negative 1 and 1. Well, that's 1 standard deviation away from the mean. We have negative 2 and 2. That's 2 deviations from the mean, 3 and 4, etc. And what we know is that the curve, in theory, extends all the way to infinity. The blue line here never actually touches the axis. In theory, it goes on forever. It's asymptotic. It never touches. So we have to keep that in mind when we're doing these kind of drawings. Now, just like the uniform continuous distribution, the area under the curve here adds up to 1. But of course, it's a curved shape, so it presents us with a little more challenge with finding certain probabilities underneath it. But the area under the curve is still 1. Now, if the area under the curve is 1, if we take exactly half of the area under the curve, well, that means that probability has to be 0.5, or 50% of the distribution. That's just a simple concept. If the entire thing is 1, half of it has to be 0.5 or 50%. Now we call this here on the right the upper bound of the cumulative distribution. So this represents the area all the way from negative infinity all the way up to a z-score or a z of 0, which is our mean. So we could write it something like this. Negative infinity less than or equal to z, which is less than or equal to 0, is 0.5. That's just an interval in our normal curve. Now how can you find that in Excel? Well, if you go into Excel and do the insert function command there at the top, you can find the norm dist function. And you can use this to find the cumulative probability in the normal distribution. That's why it's called norm dist. In this case, x is our upper bound. So our upper bound in this case is 0. Our mean is also 0 because we're using the standard normal curve where the mean is 0. The standard deviation is 1, again because we're using the standard normal curve. Cumulative is true or false. In this case, we're selecting true because we are interested in the cumulative probability up to 0. Now if you look, that gives us an answer of 0.5. If you see in the lower left there, formula result, 0.5. So we can use the norm dist function in Excel to give us the cumulative probability in any part of the normal curve. Now in the TI-83, which is what I use calculator, you can do the same thing. There's a function called normal CDF under the distribution menu, which is under the vars button. It's one of the top few there. So that means the C just means cumulative in that function. Now it requires 4 parameters. The first one is the lower boundary. Now in this case, the lower boundary is negative infinity. There is no negative infinity button on the calculator. So we use the negative e to the 99 button. And that's there in the middle of your calculator. That gives us a very large negative number. Comma, 0 is the upper bound. So our upper bound is 0, comma, the mean, which is 0, comma, 1, which is the standard deviation. So it goes lower bound, comma, upper bound, comma, mean, comma, standard deviation. And then we evaluate that in the calculator, and again we come out with 0.50000, etc. So in Excel and in the TI-83 and 84, I would assume, probably even 85 as well, calculators, you can get the same information. So I just wanted to show you how to find the cumulative probability of the standard normal curve using both. So what about this cumulative probability? So our upper bound is a z of negative 1. So z is from negative infinity up to negative 1. And how do we find that? Well, we go into Excel, we use our same norm dist. This time our x is negative 1 because that's the upper bound we're interested in. Mean is, of course, still 0. Standard deviation is 1. Cumulative is true. So when we evaluate that in Excel, we have a result of 0.1586, etc. So the probability there in the red is 0.1587 or 15.87% of the total area. Now we can do that in the TI-83 and we'll get the same thing. So normal CDF, then we have our lower bound of negative infinity. Our x, or what we're interested in, is negative 1, mean of 0, standard deviation of 1. Lower bound, upper bound, mean, standard deviation. We evaluate that in the calculator, and again, we get 0.1586, etc. So using both, we got the same answer to find the probability up to negative 1, a z of negative 1 is 0.1587. Now, if we do that for all of the z's on our graph here, and again, I'm stopping at 3, we get all of our cumulative probabilities. So if we start at negative 3, a z of negative 3, the probability up to that point, from negative infinity up to that point, is 0.00 0.3413. Now if we go on up to -2, we have 0.0228. And again, this is cumulative. We go to -1, which we just found, 0.1587. Then we go to 0. We know that that's the halfway point, so obviously it's 0.5. Then we move to the other side of the mean. Now at 1, it's 0.8413. So that's all the area up to 0.5, and then the next section of the curve. Then we keep going. We have 0.9772 for 2 standard deviations above, and then 0.9987 for 3 standard deviations above. So this is cumulative. This is from negative infinity up to each vertical section in our distribution. Now, what if we want to find the area of the interval between each section? So we found the cumulative up to each point. Now we want to find the probability between each section. Well, that's just simple subtraction. So if we want to find the area sort of in each vertical section here, we just subtract the higher one minus the lower one. So for example, if we wanted to find the probability in this area between -1 and 0, we just take 0.5 minus 0.1587, and that gives us that probability in there. So the probability that of z between -1 and 0 is 0.3413. It's very easy to do to find the probability of each section in our distribution, the space between, the intervals between the deviations. So that allows us to do several important things. You'll see this time and time again in your class. What is the probability that is between -1 standard deviation and +1 standard deviation? So this middle section here. Well, that is 0.6826. So a z from -1 to +1 is 0.6826. And if you remember, at the beginning of the video here, I showed you sort of the front page that's common to a lot of stats books. Well, this is where that 68.2% comes from. We just did it. Now, how about 2 standard deviations? So -2 on the low end, +2 on the high end. Well, when we add all those up or do some subtraction, we have 0.9544. So the probability of z between -2 and 2 is 0.9544, or 95.44%. And this is a very important one that's often used because we often use a 95% confidence in problems. So instead of 2 and -2, we often use -1.96 and +1.96, which gives us exactly 95%. But between plus or minus 2 deviations is 0.9544. And finally, plus or minus 3 deviations on either from either side is 0.9974. So that captures almost all the probability in our normal curve, plus or minus 3 standard deviations. Now notice it does not add up to 1. There is some residual probability beyond 3. Okay, so it does exist, and actually it exists forever in each direction. But for almost all the things we're going to do, we're interested in this plus or minus 3 standard deviation area. Okay, so have you seen these shapes before? Well, by now you definitely have. So what we did is just using some basic formulas or some basic functions in Excel.